Good evening, everyone. This is the masterclass looking specifically at momentum. So what we're going to be doing in this evening's masterclass is we're going to be doing a couple of really tricky past paper questions, some of which actually aren't as tricky as they look, but I think you may be surprised as to how tricky they are. All right, so without further ado, let's get started. Now, I'm hoping that you're all able to see the screen that I've got in front of you, because I was really impressed the very first time that I saw this question, because it's so different to anything I've ever seen before. It brings in vertical projectile motion, maybe. It brings in momentum, definitely, because there's a collision, but it could also bring in equations of motion, and in this case, as I said, vertical projectile motion. So the question says that a wooden block, there's the wooden block, I know it's very blurry, it says wooden block of mass 95 grams. So I'm just going to make a little note here that this is 95 grams, is freely supported on brackets. So these brackets, you could imagine they're a little bit like those things that you might use for a floating shelf or something like that, sticking out of a wall, something there that the block's on top of. But when they say freely supported, that means you can lift the wooden block on. So there's nothing gluing this in place, it's just resting on the two brackets. And it's a height of 4 meters above the ground as shown. I apologize for the quality of the image as it was. I rewrote out all the wordings so that you could see it clearly, but I wasn't going to read you the picture. Then it says a bullet of mass 5 grams is shot vertically upwards into the wooden block of mass 95 grams. It embeds itself in the block. So embeds means that the bullet's going to get into the block, and when it is, it's going to stick there. So we're going from 2 objects to 1 object. The impact causes the block to rise above the supporting brackets. So as you've got the block with the bullet in it, because of the additional upward force, the whole lot moves up together. Okay, so you've now got a bullet and a block moving upwards. Okay. The bullet hits the block with a velocity of 200 meters per second. Now, I'm telling you right away, sorry, just give me a second, there we go. All right, I'm just quickly going to make sure I mute everybody. Here we go. Okay, cool, sorted. So what happens here is that the bullet comes up and it's traveling at 200 meters per second. So since this bullet is coming up at 200 meters per second, please don't worry about air resistance and other factors here. When bullets are traveling at 200 meters per second, you can assume it's constant velocity. You don't have to work out how much it's going to slow down across the 4 meters or anything like that. You can assume that the bullet hits the block with 200 meters per second. So at the point of impact, that is its velocity. The question is, how far above the ground will the block, ooh, that should read B, that's what happens when you write things out, be at the maximum height of its path, singular. Okay, so how high above the ground, not just above the supports or the brackets, will this bullet be at the maximum height? So I really, really like this question because I think it's actually a very, very juicy question. Can I just quickly ask, I've got you guys all here. This is, I think this is the first time I haven't ever had to open up the screen multiple times. It's wonderful. So can I just quickly ask at this point, who's seen a question that looks anything like this before? Okay, I hadn't either until I saw it. Ooh, Nasia's seen it. Okay, now when I say like this, have you seen things going upwards? I've seen things going across to the side, but I've never seen a bullet fired into a block making it go upwards, which is a really interesting question. Okay, so Nasia just said also to the side. So when things move up, it definitely makes it a little bit more interesting in terms of exactly what's happening. All right, so what I'm going to do now, I've already paused my screen, is I'm going to give all of you an opportunity to do your very best to calculate this answer. I know it is not a very easy question to do, so please don't panic if you can't do it, but give it a go. As a hint, you're going to start off by doing law of conservation of linear momentum, 2 separate objects to 1 object with a bullet embedded in it. And then after that, you're going to use equations of motion to get the maximum height. Okay, is everybody good to give this an attempt on their own? Everybody happy with that? Good luck. Okay. Only one person looks like they're good. Hopefully not a problem. Please give me a thumbs up as soon as you're done. I'm not near done, just in case you're worrying, but let me know when you're done as well. You may need to look up your equations of motion here. Okay, just be warned, you're going to have to quickly go and find the equation that you need. Okay, we got one person who's already got the answer. Well done. Okay. Good, well done. Okay, can we just take a step back? Can anyone, okay, brilliant. We're just waiting on one last person to get to the answer. Normally in a masterclass, I don't have the opportunity to see everyone to know who's done it. So that's great. Okay, so over here, if everyone wants to check the velocity that you should have got of the bullet and the block together should have been 10 meters per second upwards. Okay, so if you've got that, that tells me that you've done the first part, which is the conservation of linear momentum. That has been done correctly. After that, you've got to use your equations of motion to figure out how high it goes. Okay, now I don't know if anyone's brave. Does anyone want to quickly type in what answer they got? Good. Okay. Good, good. I'm very impressed. I thought you guys would forget to add on the 4 meters from right at the beginning. So anyone who didn't add on the 4 meters, please remember it was already 4 meters above the ground before it started moving upwards. Okay, I assume at this point, I think we've had long enough on this question, so I'm going to resume sharing so that everybody can see my methodology and working out. Please make sure that you're getting into very good habits with your layout. I know I'm sometimes a little bit right here, right here, right here, and I write all over my screen, but I promise you when I write out stuff in an exam, everything's usually underneath each other, or at worst, I have 2 columns on my sheet, and they're clearly differentiated as to what I'm doing where. Okay, don't leave us with the dog's breakfast to try and figure out. So please, you need to have an equation. Sum of momentum before must equal sum of momentum afterwards. Usually when we mark it, it's 1 mark for either of those two, but don't forget the sigma sign, okay? If you just write momentum before equals momentum afterwards, not necessarily going to get the mark. Then it's substitution. Don't forget that even if you know it's 0, you must sub it in. So I would say here it's 1 mark for that side, 1 mark for this side. And technically, I'm going to say there isn't a mark for that 10, but there is a substitution mark for you substituting it in. Because we did not know what the time was, the logical choice of equation of motion is this one up here, because then it doesn't have delta t. So 1 mark for formula. If you didn't see that and you used another equation of motion or 2 equations of motion to get to the same answer, you still get your marks. I've already given you a substitution, so I'm going to be very generous. 1 substitution that side, 1 substitution for the 0 squared. So nice. And then right at the end, there's going to be 1 mark. Sometimes they're nice and they give you a bonus mark for adding the 4, but I think I'm going to go straight to answer. So this is 1, 2, 3, 4, 5, 6, 7. I don't think this was the hardest question I've ever seen, but it definitely involved many different parts. And I think because it's different to what you're used to seeing, some of you may get confused as to whether this is vertical projectile motion or momentum, or in fact, as it is here, a case of both. So I've seen questions where objects are thrown up and they come back down and then they crash through glass, and you've got to work out the impulse when they're crashing through the glass and those kind of questions. This is, I guess, probably going to fall into a similar category, but I just found it to be a really interesting question. All right, who liked that one? Liked as in found it a little bit, I guess, challenging, good challenging. Yeah. I'd have loved to put that in a prelim paper. I really would, but you guys have got the advantage. I'll only be able to go into a prelim paper in about 3 years' time. All right, so let's move on. If you need any screenshots, please take them right now. Okay, onwards to the next question. Where are we? Ah, here we go. Okay. I wasn't certain if I'd given you this question before, but I decided that we'd done something similar, but not this exact version. So I thought we'd go back and quickly have a look at it. So hopefully everybody can see this now. I'm just going to quickly zoom in a bit. So it says that the same force, magnitude F, is applied to trolleys A and B alternately. So it's applied to trolley A, then to trolley B, or you could imagine it's applied to trolley A and B, but each of them get their own force F at the same time. The force, the mass of trolley A is twice that of trolley B. So I find that I always do this. If it's twice the mass, it's 2m, and this one is m. And the trolleys are on a frictionless surface. As soon as we've got frictionless, we don't have to worry about them slowing down. They're just going to carry on moving at constant velocities. unless they hit each other or momentum changes or something like that. If the rate of change in momentum of trolley A is X, then the rate of change of momentum of trolley B will be. All right, I'm going to quickly pause this and I'm going to give you a chance to select your answer. I must be honest, in this case, I already know which one's mine, but I'm going to give you a chance to work it out. Go for it. It's not as tricky as you might make it. Okay, give me a thumbs up when you're done with that, please. Okay, well done. Well, I hope it's well done. We'll wait and see if they're all right. Well done on getting it done. Okay, so I find in some multiple choices, I work by eliminating wrong answers. In ones like this, I don't eliminate wrong answers. I do a quick figuring it out. So we're now going to quickly check who got it right. Who said that their answer was A? Give me a thumbs up if you went with A. Who said their answer was B? Who said their answer was C? Who said their answer was D? Okay, somebody didn't have an answer at all. In this particular case, not one of you got it right. So it's a good question. The answer is X. And the quite simple thing is that your equation for the rate of change of momentum, if you use the equation F delta T is change in momentum, then we can say that force is equal to the rate of change of momentum. And the force for both of them is the same. So if that is equal to your rate of change of momentum and that is equal to your rate of change of momentum, both of them are going to be the value B. Now, where many of you get caught out with these kind of trolley questions is that you are doing funny things where you suddenly start thinking momentum is mass times by velocity, and oh, suddenly this has got to be V and this has got to be twice the V, and you're getting so caught up in mass and velocity, and now one goes up and the other goes down, you forget to answer the question. So you need to remember with examples like this, that if we have a system where everything collided and then split apart, or there's an explosion and things move outwards, that's the other similar version that they do with this. They have two trolleys together, and one's mass M and the other's mass 2M, and there's a huge explosion, and then they move apart from each other, and M goes this way, and 2M goes this way. I think we even did this one in one of the lessons, but it's important. And then they go and ask you, if this has a momentum, so if the momentum of this one is X, or the magnitude of the momentum is X, what is the momentum of this one? And your answer should be, well, the law of conservation of momentum says that the momentum of the system before was 0. So the momentum afterwards must be 0. So this must be negative X. The only time that it may be X is if they ask you for just the magnitude. So if they said, what is the magnitude? Then both of them are X. If they ask you, what is the momentum? Then you change it to a negative X. Please just be aware of that. As I've already said, some of you get so caught up in doing this is V and this is 2V, and then you're doing calculations that are way out there instead of just focusing in on where you should be. All right. Does this make sense to everybody now? Do you at least understand where you went wrong in terms of your thinking or approach to it? I find with a lot of these type of questions, I start by trying to find the equation that links to the relationship that they're talking about. Because often once you find and isolate and write down that equation, the answer becomes very clear. And it's also sometimes not the answer you'd have expected. So there's a very good chance you'd have been expecting it to have two different values because they're different masses. But you've got to always have a look at it and make sure that you're being very careful about it. All right, so let's clear that and then move on to the next question. I think I may have to zoom in to get this one nicely in the screen. Okay, I don't think we did this one in the previous lesson. Please, if we did, you need to just correct me. But I actually had this set out to do, and then I don't think we got there. If I recall correctly, that's how I remember this being. Okay, so yeah, if you're experiencing deja vu, I'm in a bit of a holiday mode at the moment. I'm sure some of you are too, with the week off. So just double check. Okay, so our question here says a metal pendulum bob of mass 10 kilograms. Just in case anyone doesn't know what a pendulum is, it's a mass piece on a piece of string or a thread, and it moves in an arc backwards and forwards like this. So if you pick it up and it normally would dangle here, and you pull it across, when you release it, it's going to swing around. Any mass, like this could literally be a ball of clay. The proper ones that they do are metal balls with just this tiny little ring on the top that you tie the string onto. So it has a mass of 10 kilograms and it is attached to an inelastic rope. Important thing about the word inelastic is the length from here to here remains the same at all points along here. So it's always going to be the same length. The reason that's an important thing to note is that sometimes you end up having to do weird things with trig and angles, and it helps if you can know that that length and that length is still the same when you do little weird right angle triangles and other fun things. So it is held stationary at position A. That tells me that the velocity is 0 meters per second at a height of 5 meters above the ground, as shown in the sketch below. When the bob is released, it swings to position B, striking a stationary crate. So we've got a velocity of 0 of unknown mass, so we don't know what the mass is, and the crate moves to the right at a speed of 2 meters per second. The pendulum bob rebounds, that means it moves back this way and swings back up, and then it reaches a lower height of 1 meter at position C. Ignore all frictional forces, so you don't have friction. Now, when they say all like that, it's air friction for the pendulum bob, and it's also for the crate that there isn't friction against the ground. So there isn't any friction here between the crate and the ground. Okay, so I think this question's a really, really nice one. You'll probably find you're already sitting there with your brain a little bit confused about how it's coming in, bouncing back, and what's happening everywhere, because there's a lot happening. So we're going to get started, and I'm going to ask you quickly to do 4.1, 4.2, 4.3. Okay, you've managed all of those. 4.4 shouldn't be that far away, but I'd like to check in before you jump onto 4.4 once you've done those three. All right, everybody good to start this? Quickly give me a thumbs up so that I know. Okay, brilliant. Go for it. It's also testing your work, energy, and power a little bit. I've gone one step way too far. Oopsie. The point where you realize you've got to the end and the question wasn't calculate the velocity, it was calculate the kinetic energy. So please, a little bit of a heads up. Don't do what I've just done. Make sure that you stop before you break it. It's always a good idea also, once you got to your answer, to just go back and check that you've answered the question that was asked. All right, my goodness, that was a tricky one. All right, so can I ask, as soon as you've answered those three, that you let me know? Okay, don't worry if you're stuck with 4.3, it's multiple steps. So what I did with 4.3, can I just ask, how did everybody do in 4.1 and 4.2? Okay, so to just quickly give you an idea, with 4.1, you were asked to state the principle of conservation of mechanical energy in words. And my answer was that the total linear momentum of an isolated system remains constant. Okay, I'll put up my solutions just now. When I calculated the kinetic energy of the pendulum bob, I got an answer. And I'm in fact going to do something I've recently started doing that actually works relatively well. Okay, just give me a second. That's so I can delete my workings so that I can share what I've got and then put it back. All right, so what we're going to be doing here is we're just quickly, you can hopefully see my answers here, quickly going to go through the first two questions and then I'll put it back in my writing for the last one. So the question here, state the principal conservation of mechanical energy. The key words you need are total, linear, momentum, isolated system, and then something about remains conserved, stays the same, does not change, anything conserved. Ideally, remains the same or is conserved, probably not remains conserved. That should be is conserved, either way. Show that the kinetic energy of the crate at point B is 392 joules. Now, very importantly here, a lot of students get into lazy habits where you say potential energy at the top equals kinetic energy at the bottom, and you immediately throw away all of your marks, okay? There is no rule that says potential at the top equals kinetic at the bottom. What the rule actually is that the mechanical energy at the top equals the mechanical energy at the bottom. And it happens to be a case that at the top, quite often, your kinetic energy is 0. And at the bottom, quite often, your potential energy is 0. But if you take shortcuts in a matric exam, I can promise you that you're going to end up losing a huge number of marks. Okay. So, sorry, there's just a quick question I have to go back to. Somebody asked, are they asking for the conservation? Oh, damn, I'm being silly. Okay, the principal conservation of mechanical energy says that the total, brain died, the total mechanical energy of an isolated system remains conserved. Please don't do what I just did. It's one of those most common things that you just blurted out and they're both conserved. I mean, all that I had to do here was change the word linear momentum into mechanical energy and it's still okay. All right, thank you for pointing that out just as well. And I felt very bad if that went out later. So conservation of mechanical energy. Don't write momentum in a test because you'll lose both marks. Oops. Okay. Sorry, I was so busy focusing on getting to the question. For the next one, where it says calculate the kinetic energy here, please, you had to indicate that it was both potential plus kinetic equaling potential plus kinetic. You're going to lose more than just a formula mark if you did a shortcut here. You would get the same answer, but you wouldn't even get a mark for the answer, I don't think. Okay, because you're using completely inappropriate principles. So please, I'm begging you right now, make sure that you're not lazy. Did everybody get that answer over here of 490 joules? Okay, fantastic. Now the next question asks us to work out the kinetic energy of the crate at point B. And this is a bit weird, but what we're going to be doing here is saying that the mechanical energy of the box and the crate before they collide must equal the mechanical energy of the box and the crate after they collide, because we were told at all points that we could ignore frictional forces. So we're going to do a bit of a weird thing where we're going to say, so this is going to be the kinetic energy of the crate at point B, which is where they have just collided. So just after they've collided. So this one here was just before they collide. This here is going to be as they collide. Remember, the crate originally was stationary. It only starts moving afterwards. So what I did here was I worked out the mechanical energy of the pendulum at point B, which is its kinetic energy of 490 plus its potential, which I'd work out nicely, but it ends up being 0. Okay, and all of that must then go to be the same mechanical energy a second later, like a fraction of a second later, once we've moved to the pendulum having rebounded to point C and the crate moving off towards the right. Okay, a little bit of a weird one. Does anyone want me to go through it immediately with them, or do you want just a second to try and do that by yourself? I know I've given you 2 options in one go. Who'd like me to go through it immediately? Just quickly undoing so that I can hopefully get my original writing back. There we go. All right, so you all want a second then to do it, I presume. I'm going to quickly go. All right, one person wants me to go through it. I'll go through it in just a second. I'm giving everybody else a quick chance to try and finish it. And you will know that you're right if you get an answer of 392. The reason they gave you the 392 is that if you didn't get it, you can still use that value in the next part. Okay, so you can still use it to then calculate the mass. Okay, please give me a thumbs up when you want us to continue. Okay, one person wants us to continue. The rest of you, you're nearly done. I don't know if I'm waiting or if you've given up on this one. Okay, nearly done. We got one person who I think is now nearly done. I have misinterpreted that again. Okay. Okay, brilliant. Okay, I think given the time, I'm going to quickly go through this one with you now so that we have enough time to make sure that we finish this properly and then possibly even get on to the next one. All right. So let's have a quick look at what I did. Please note, I was a little bit quick here because you probably should have gone into a little bit more detail, but I didn't have lots of space, so I did shorthand to make it faster. Please don't. So I couldn't put mechanical energy before and after in one line and make them equal to each other. I had to do them on separate lines. So I said that the mechanical energy before they collide is the mechanical energy of the pendulum plus the mechanical energy of the crate. The mechanical energy of the pendulum, I cheated. I knew it was that value, so I stuck in the whole 490. Here, please, for the mechanical energy of the crate, you probably would have done well to do mgh plus a half mv squared and subbed in a whole bunch of zeros. That's what you should have done. But either way, the mechanical energy before was 490 of the pendulum and 0 for the crate, so 490 total. Afterwards, the mechanical energy was the mechanical energy of the pendulum as it rebounded back, plus the mechanical energy of the crate. So I said my 490 was potential plus kinetic for crate, potential plus kinetic for pendulum. So then I said the 490 was mgh plus the kinetic energy. I didn't break this up because otherwise I'd have ended up with a problem. Plus the mechanical energy of the pendulum, the kinetic energy when it reaches this highest point is again going to be 0. You should in fact have gone a half mv squared and subbed in zeros, etc. But I'm doing a shorthand. Don't do that in an exam. So 490 is 0 plus kinetic energy plus 10 times 9.8 times 1 plus 0. So the kinetic energy is 392 joules. Okay, so the kinetic energy is just 392 joules, which is the answer that we expect to get there. All right, who managed to get that on their own? Well done. It takes a little bit of knowing where to start and kind of what to do, but I find that as always, the more you practice, the faster you see it. And sometimes in an exam, it just takes a little bit longer for you to see what your step is. Okay, question 4.4, I'm going to quickly ask you to calculate the mass of the crate. It should not take you very long at all. Please, if you didn't get the answer of 392 joules, you are still welcome to use it because they gave it to you. Okay. It's quite a big, heavy crate, I think, but yeah. All right, have you got the answer for the mass of the crate yet? Good, good, fantastic. All right, so the answer that I got for the mass of the crate was 196 kilograms. Kinetic energy is a half mv squared. Just use the 392. Please be very careful. It gets very silly if you use the 490, and some people probably will. So yeah, if you use the 490, it doesn't work so well. Okay, so just make sure that you go and use the correct value. All right, so I'm going to quickly clear everything here so that we can continue with the second part of this question. Okay, the second part of the question, which you can now see a little bit clearer because it's moved down just a little bit, says after moving a short distance, crate X, which remember was moving at 2 meters per second, and remember over here it had a mass of 196 kilograms, collides with a second crate Y of mass 150 kilograms. I always find that I like writing the values onto my picture so that I don't miss anything later. It's moving to the left at 0.5 meters per second. After the collision, there's the collision, crate Y moves off to the right with a speed of 1 meter per second. So the first question, and I did preempt this earlier, I think maybe that's why momentum was on my mind, was state the principle of conservation of linear momentum in words. So it would be exactly the same as the answer over there. I'm not going to make us spend time doing this. Be that the total linear momentum of an isolated system remains constant. I think we're all good with that. And then the question that I want us all to do is to calculate the velocity of crate X immediately after the collision. I'm going to quickly ask you to do this as a hint in case you have any doubts about this. Anytime you're ever asked to state a principle, you're likely to use it in the next step. Okay, it's very, very uncommon. I don't think I've ever seen it where they ask you to state a principle and it has nothing to do with the next step that you take. Okay, so I'm going to pause, go for it. All right, please give me a thumbs up when you've got to an answer. Fantastic. All right, now while we're just quickly waiting for someone, one of the things I wanted to discuss with this particular question is, let's say that you couldn't, for whatever reason, figure out the mass of the crate in question 4.4. I hope you do all realize that if you kept the mass M, I think here in this particular case, we could have still substituted in a mass M. I'm trying to work, and it should, I think, have worked, although we'd have had two variables, so maybe not. Okay, I was going to say I'd still have tried to do as much of this as I could just using a mass M. Okay, some equations, they actually cancel out rather nicely, and you don't need to know what the mass is, but I don't think this is one of them. Okay, brilliant. Everybody done? So I got an answer of 0.85 meters per second to the right. So I said the sum of momentum before is equal to the sum of momentum afterwards. M1 V1 plus M2 V2 initial is M1 V1 plus M2 V2 final. Subbed in all my values. Please, the important thing was to pick a direction as positive and stick with it. Anything in the opposite direction is therefore negative. And lastly, I got right to the end and I solved for my answer. Did everybody get the same question? Did you get the same answer? Okay, well done. All right. So that's a nice, neat one. Okay, last thing over here, let me just quickly go and find it, is that we're now going to go to this question. All right, so this question over here, oh, let's go back to writing pen. There we go. Says the bounce of a cricket ball is tested before it is used. Okay, so I don't do too much on this, but you've got to have a certain amount of bouncing things, sports equipment, testing stuff. Okay, so the standard test is to drop a ball from a certain height onto a hard surface and then measure how high it bounces. During such a test, a cricket ball of mass 0.15 kilograms is dropped from rest from a certain height and it strikes the floor at a speed, oh, sorry, I don't know why I got there. That should be the speed of 6.2 meters per second. The ball bounces straight upwards. So I'm going to draw this as going down and then up, purely because if I made it in a straight line, you wouldn't see what I was drawing. And it bounces straight upwards. So it hits the ground going at 6.2, bounces up at 3.62 meters per second. And when it bounces up, it reaches a height of 0.65 meters. We assume it was dropped from a higher height than that at the beginning. Okay. The effects of air friction may be ignored. First few questions. Define the term impulse in words. Some of you may find that a little bit harder than you realize. And then the question is to calculate the magnitude, so only size, of the impulse of the net force applied to the ball during its collision with the floor. I'm going to ask everybody just to do those first two, and then we're going to check in again. All right, please go for it. Okay, please give me a thumbs up when you're done with that. Well done. Okay. Good. I think given the fact that we've only got 5 minutes left, I'm going to share the answer now and then we can have time to do the last one. Okay, brilliant. And you're all done anyway. So what we had to do here was the term impulse. The definition of it is that it is the product of an applied force and the duration of the time that it is applied for. Keywords you need are product, force, and time. You may get away with saying applied force or resultant force. We're not too fussed about the force, but it's got to be the product of the force and the time of the application. Please be careful. I don't know why, but a few years ago, there were a large number of students who just said the force and the time, and they left off the word product. So if you say a force is applied for a length of time and you don't mention the word product, you don't have a mark. Okay. Calculating the magnitude of the impulse. Well, you've got to remember that this side of the equation is your impulse. So impulse is the product of force and time, and that is going to equal the change in momentum. Okay, so when we break up our change in momentum, it is the mass multiplied by the final velocity the mass multiplied by the initial velocity. So one of the very important things to do here is to make sure that you kept your signs correct. So you had to realize that we had a final velocity of 3.62 and an initial velocity of 6.2. If you chose downwards as positive, you'd have this being negative and that being positive, so you had to have a minus minus. If you chose your signs to be the other way around, you'd have had a plus and then a minus minus, which made it a plus. Either way, your answer is 1.4. In fact, you could have got away with just 1,47 Newton seconds. Please, because the question asked us for impulse, you're not going to answer in kilogram meters per second. You're going to answer in Newton seconds. Okay, very important. All right, so we're just going to do one last question and then we're going to be done with the momentum section. Okay, so I'm just quickly going to move on to the last one. It says to meet the requirements, the cricket ball must bounce to 1/3 of the height that it is originally dropped from. So what we need to do here is we need to quickly work out whether or not the ball meets the minimum requirements. We've got very little time left, so I'm just quickly going to pause this. Okay, you're going to quickly go and see if you can work this out. As a hint, you know how fast it is traveling when it hits the ground, and you know that it must have stopped, there we go, started with a velocity of 0. Okay, so I'm going to quickly, I'm in fact going to clear all of my impulse notes because you don't need them, but get going. Won't make a difference to you. Okay, quickly answer that question. Try to avoid taking any shortcuts, even though we're hurrying a little bit, I know. Okay, can I quickly ask if anyone's managed to get the height? Just quickly put it in the chat column so that I can double check whether we're good. Okay, just quickly put it in there so we can check. Okay, good. I got the same as you. All right. Okay, no, I agree with Nasia's answer. All right. Okay, perfect. Good. All right, so we're just at the end of our time before we start on the next class. So let's just quickly go into here. What I did was I said that the mechanical energy at the top equals the mechanical energy at the bottom. So potential plus kinetic equals potential plus kinetic. And then at the top, the mass was 0.15. We had 9.8. We don't know what the height is, but it wasn't yet moving. At the bottom, it had no height to hit the ground. It was traveling at 6.2 meters per second squared, sorry, meters per second downwards. So I did my calculation and I got 1,96 exactly. Now this is where things get very technical. If I take 1.96 and I divide it by 3, I get an answer of 0.65, which if you round to 2 decimal places, you're yay, it's high enough. But if you put in that 0.3 meters, it doesn't get there. So I must be honest, I'm pedantic enough here that my answer would be no. And the reason is that it does not reach the full value of 0.653 meters. It only reaches 0.65 meters. I'm willing to bet that in the particular year that they did this, they really regretted not making it that clear cut, because if a student rounded up anywhere en route, they would be able to state that it did reach it. And some of you who said that it did reach it, who looked at it and said 0.653 is 0.65. Okay, now I think it comes down to one of those things where if I go and tell you that something in the shop costs 60 Rand and I've got 59 Rand 99, can I go and buy it? Many people will say, well, yeah, you got 60 Rand, but you don't. So I would be pedantic about this and say it's not good enough, it's not close enough. All right, okay, I'm going to quickly stop sharing. I hope that you all really understood that one and that it made good sense to you. Please make sure that you keep practicing your momentum. All right.